Hello everyone. Today we are going to analyze this beam using slope deflection method. Before analyzing, let us see the beam one time. In this beam, there are three spans: span AB, span BC and span CD. In the span AB, we are having point load 24 kN acting on the center. In the span BC, we are having UDL 12 kN per meter acting for the full span. In the span CD, we are having a point load 25 kN acting at 3 meter from the point C. In the point A, there is a fixed support. In the point B, in the point C, and the point D, we are having hinged supports. The moment of inertia for the span AB is 2I, for the span BC it is 1.5I, and for the span CD it is 2I. Length of the span AB is 4 meter, length of the span BC is 3 meter, and length of the span CD is 5 meter. In the slope deflection method, we have to find the number of supports in which slope can occur. Let us see the conditions. In the fixed support, there will be no slope. In the hinged support, there will be slope. In the roller support also, there will be slope. In this beam, there are three hinged supports. In the point B, in the point C, and in the point D, we are having hinged supports. So, the number of supports where slope can occur is equal to 3. In the point B, we are having theta B. In the point C, we are having theta C. And in the point D, we are having theta D. So, there are three unknowns in this problem. If we calculate these three unknowns, we can easily find the final moments. To calculate these three unknowns, we need three equilibrium equations. Let us see how to make equilibrium equations. The equilibrium equations can be made in the ends and joints of the beam. In the joints, the summation of the moments will be 0. Then we have to check the end conditions. In the fixed end, there will be moment. We cannot make equilibrium equation. In the hinged end, there will be no movement, so we can make equilibrium equation. In the roller supported end also, there will be no movement, so we can make equilibrium equation. In this beam, first let's see the ends. In the point A, we are having a fixed support. In the fixed support, there will be a movement, so we cannot make equilibrium equation. Now let us check another end D. In the point D, we are having a hinged support. In the hinged end, there will be no movement. So MDC is equal to 0. This is our first equilibrium equation. Then let us see the joints. There are two joints, joint B and joint C. In the joint B, there are two moments, MBA and MBC. When we add these two moments, it will be 0. This is our second equilibrium equation. In the joint C also, there are two moments, MCB and MCD. When we add these two moments, it will be 0. This is our third equilibrium equation. In this analysis, there are three unknowns. To find out these three unknowns, we needed three equilibrium equations and we have formed them. In this beam, we have to calculate 5 moments: MAB, MBA, MBC, MCB and MCD. Also, we have to find 4 vertical reactions: RA, RB, RC and RD. Now, let us calculate the fixed end moments. For calculating fixed end moments, we have to assume every span as a separate fixed beam. First, let us take the span AB and assume that it is a separate fixed beam. Now let's see the formulas to calculate the fixed end moments. Here you can see some of the important fixed end moments for the different type of loadings. In the span AB, there is a point load acting on the center, so we have to select this condition. The formulas are minus WL upon 8 and positive WL upon 8. In the span BC, there is UDL acting for the full span, so we have to select this condition. The formulas are minus WL square upon 12 and positive WL square upon 12. In the span CD, there is a point load. That point load is not acting on the center, so we have to select this condition. The formulas are minus WAB square upon L square and positive WA square B upon L square. Now let's apply these formulas and find out the fixed end moments. In the span AB, there is a point load acting on the center. We have already seen the fixed end moment formulas minus WL upon 8 and positive WL upon 8. M of AB is negative because it is acting in the anticlockwise direction. M of BA is positive because it is acting in the clockwise direction. Let us apply the values inside the formulas. W is 24, L is 4. When we apply the values inside the formulas, we are getting M of AB is equal to minus 12 kilonewton meter and M of BA is equal to 12 kilonewton meter. In the span BC, UDL is acting for the full span. We have already seen the fixed end moment formulas minus WL square upon 12 and positive WL square upon 12. Let us apply the values inside the formulas. W is 12, L is 3. After applying all of the values inside the formulas, we are getting M of BC is equal to minus 9 kilonewton meter and M of CB is equal to 9 kilonewton meter. Now let us calculate the fixed end moments in the span CD. In the span CD, we are having a point load. This point load is not acting on the center. We have already seen the formulas for the fixed end moments minus WAB square upon L square and positive WA square B upon L square. Let us apply the values inside the formulas. W is 25, A is 3, B is 2, L is 5. After applying the values inside the formulas, we are getting M of CD is equal to minus 12 kilonewton meter and M of DC is equal to 18 kilonewton meter. Now let us make slope deflection equations. First, let us make in the span AB. We have already calculated the fixed end moments. Let us apply the values. In the point A, we are having a fixed support. In the fixed support, there will be no slope. So theta A is equal to 0. Let us cut theta A and make it as 0 in both of the equations. In the span AB, length is 4 meter. Let us apply. The moment of inertia is 2I. So instead of I, we have to apply 2I in both of the equations. Finally, we are getting two equations. Now let us make the slope deflection equations in the span BC. Let us apply the fixed end moments. In the span BC, length is 3 meter. Let us apply in both of the equations. The moment of inertia is 1.5I. So instead of I, we have to apply 1.5I in both of the equations. After the calculations, we are making two slope deflection equations. Now let us make slope deflection equations in the span CD. The span CD is 5 meter long. Let us apply that in the equations. The moment of inertia is 2I. So instead of I, we have to apply 2I in both of the equations. In this equation, let us make the first equilibrium equation. We have already seen in the point D, there will be no movement. So MDC is equal to 0. Instead of MDC, let us apply 0. Then let us take this 18 on the left side. It will come as negative. This is our first equilibrium equation. We have made one equilibrium equation, but we need three equations. We have already seen that the second and third equilibrium equations can be made in the joints B and C. In the joint B, MBA plus MBC is equal to 0. We have already made the slope deflection equations for MBA and MBC. Let us apply that. 12 minus 9, we will get 3. Let us take 3 on the right side. It will come as negative. Then let us add these two values. After adding, we are getting 4 theta b. Finally, we have made the second equilibrium equation. Let us keep this equation as number 7. The third equilibrium equation can be made in the joint C. In the joint C, MCB plus MCD is equal to 0. We have already formed the slope deflection equations for MCB and MCD. Let us apply them. 9 minus 12, we will get minus 3. Let us take it on the right side. It will come as positive. When we add these two values, we will get 3.6 EA theta C. Finally, we have made the third equilibrium equation. Let us keep this equation as number 8. Finally, we have made three equilibrium equations, the sixth one, seventh one, and the eighth one. Now let us use the calculator and solve these equations. If you do not know how to use calculator for solving three equations, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and found the answers. Now let us apply these unknowns in the slope deflection equations and find out the final moments. When we apply the value of A theta b in the equation number 1, we are getting MAB. When we apply the value of A theta b in the equation number 2, we are getting MBA. When we apply the values of A theta b and A theta c in the equation number 3, we are getting MBC. When we apply the values of EA theta b and EA theta c in the equation number 4, we are getting MCB. When we apply the values of EA theta c and EA theta d in the equation number 5, we are getting MCD. In this analysis, we have calculated all of the moments. For MAB, we are getting a negative value. That means MAB is acting in the anticlockwise direction. For MBA, we are getting a positive value. That means it is acting in the clockwise direction. For MBC, we are getting a negative value. That means it is acting in the anticlockwise direction. For MCB, we are getting a positive value. That means it is acting in the clockwise direction. For MCD, we are getting a negative value. That means it is acting in the anticlockwise direction. Now let us calculate the vertical reactions. First, I am going to take the span AB and calculate the vertical reactions. In the span AB, there are two moments, MAB which is acting in the anticlockwise direction and MBA which is acting in the clockwise direction. In this span, first I am going to calculate RA. For that, I am going to take moment about B. In this case, I am moving towards right hand side. Clockwise will be positive and anticlockwise will be negative. The vertical reaction RA is acting towards the point B in the clockwise direction, so it will be positive and the distance is 4. So for RA, the point load is acting towards the point B in the anticlockwise direction, so it will be negative and the distance is 2 meter, so minus 24 into 2. Then we are having two movements. This movement is acting in the anticlockwise direction, so it will be negative, and this movement is acting in the clockwise direction, so it will be positive. Finally, we are getting RA, which is equal to 13.37 kilonewton. Now we can easily calculate RB1 by applying the rule summation of vertical forces is equal to 0. In this span, we are having three loads, RA, RB1 and 24 kilonewton. RA and RB1 are acting upwards, so both are positive. 24 kilonewton is acting downwards, so it will be negative. We have already calculated RA, we can apply that. Finally, we are getting RB1 is equal to 10.63 kilonewton. Now, let us take the span BC and calculate the vertical reactions. In the span BC, there are two movements, MPC which is acting in the anticlockwise direction and MCB which is acting in the clockwise direction. In this span, first I am going to calculate RB2. For that, I am going to take moment about C. RB2 is acting towards the point C in the clockwise direction, so it will be positive and the distance is 3 meter, so 3 RB2. The UDL is acting towards the point C in the anticlockwise direction, so it will be negative. For the UDL, we have to multiply with the distance and distance by 2. Here the distance is 3 meter, so 3 into 3 by 2. Then we are having two movements. 8.34 is acting in the anticlockwise direction, so it will be negative. 15.81 is acting in the clockwise direction, so it will be positive. Finally, we are getting RB2, which is equal to 15.51 kilonewton. Now, using the rule, we can calculate RC1. RB2 and RC1 are acting upwards, so they will be positive. UDL is acting downwards, so it will be negative. For the UDL, we have to multiply with the distance to get the total load. So 12 into 3, we have already calculated RB2. Let us apply that here. Finally, we are getting RC1 is equal to 20.49 kilonewton. Now let us take the span CD and calculate the vertical reactions. In the span CD, there is only one movement, MCD, which is acting in the anticlockwise direction. In this span, first I am going to calculate RC2. For that, I am going to take moment about D. RC2 is acting towards the point D in the clockwise direction, so it will be positive and the distance is 5 meter. So 5 RC2. The point load 25 kilonewton is acting towards the point D in the anticlockwise direction, so it will be negative and the distance is 2 meter, so minus 25 into 2. This movement is acting in the anticlockwise direction, so it will be negative. Finally, we are getting RC2, which is equal to 13.16 kilonewton. Using the rule summation of vertical forces is equal to 0, we can calculate RD. After calculations, we are getting RD, which is equal to 11.84 kilonewton. In the point B and in the point C, we have calculated the reactions two times. For RB, we have to add RB1 and RB2. Finally, we are getting RB. For RC, we have to add RC1 and RC2. After adding, we are getting RC. Now, we are going to draw the shear force diagram. Before drawing the shear force diagram, let us calculate the shear force values. I am going to calculate the values from the point A towards the point D. In this case, I am moving towards right hand side. upwards will be positive and downwards will be negative. Using the concept, I have made the calculations. After making the calculations, we can draw the shear force diagram. Now we are going to draw the bending moment diagram. Before drawing the bending moment diagram, we have to make the free moment diagram and the end moment diagram. Then we can combine both of them to form the bending moment diagram. For making the free moment diagram, we have to consider every span as a separate simply supported beam. First, let us take the span AB. If in the simply supported beam, point load is acting on the center, the formula to calculate the maximum bending moment is WL upon 4. Here W is 24, L is 4. When we apply in the formula, we are getting 24 kN meter. If in the simply supported beam, UDL is acting for the full span, the formula to calculate the maximum bending moment is WL square upon 8. Here W is 12, L is 3. When we apply in the formula, we are getting 13.5 kN meter. In the span CD, we are having a point load. This point load is not acting on the center. The formula to calculate the maximum bending moment is WAB upon L. Here W is 25, A is 3, B is 2, L is 5. When we apply all of the values in the formula, we are getting 30 kN meter. For the point loads, the diagram will be in the shape of a triangle. For the UDL, the diagram will be in the shape of a parabola. Now let us make the end moment diagram. Using the end moments, we have to make the end moment diagram. To mark these values above the line or below the line, we have to see the direction of the curves. All the curves are indicating upwards. That means all the points in the end moment diagram will be coming above this line. In the point B, we are having two moments. In the point C also, we are having two moments. Even though we are having two moments, we have to make only one point because both of these arrows are indicating upwards. In the point C also, both of these arrows are indicating upwards. If the end moment diagram comes above the line, it will be negative. If it comes below this line, it will be positive. Now let us combine the free movement diagram and end movement diagram. Wherever they are acting alone, without mingling with each other, we have to mark the values with the sign. Here end movement diagram is acting alone. Here free movement diagram. Here end movement diagram. Free movement diagram, end movement diagram, and free movement diagram. Wherever they are acting together, we are not marking anything. We just keep the space empty. Now we are going to end this session. Thank you for watching this video.